Good afternoon, everyone. Thank you for coming to our work session. So today, we're going to talk about the platform hardware error handling. I'm David Shao from Facebook. This is Anil from Intel. Unfortunately, we have one member, Zhengyu, because of some visa issue, cannot join. Okay. Too fast. Okay. So this is today's agenda. So I'll start with some of the Facebook data center operation and what are the pain points during this operation and what do we see from the error handling point of view. And then I'm going to talk about based on those pain points, what are the error handling requirements from our view. And then with an example, Anil will start talking about the Edik error detection and correction driver and the enhancement. And then he will start with the future efforts that the community can all work together. Okay. So hardware error. I think sometimes hardware error is a good thing. It's a job security for a system engineer, like someone like this. But I don't like errors. And I don't think anyone likes errors in operation. However, hardware will always fail, and hardware errors always happen. Large-scale data center make the things worse because large volume of the server and also huge amount of components. In this case, hardware error handling becomes more and more important nowadays. So during Facebook, our own operation in data center, we observed the three major pain points. The first one, system performance degradation due to the error handling mechanism, especially when there's a large amount of errors flood in. Second one, no trouble found in RMA. The high no trouble found NTF rate always reduce the operation efficiency. The last one, but not the least, failure mitigation scaling. We can always patch or apply workaround for a specific platform. But how can we make this scalable across different platforms? And by doing this, it will greatly help operation team to smooth the operation cycles without firefighting. So I think with the server platform, server volume keep growing. This is a shared problem within OCP community. And we like to encourage everyone to think about it, and then we can work together. We expect with the shared problem, probably there are some shared solutions we like to see. So let me go to the next one. Okay. Before we go to the detail, if we look at the hardware error handling overview, for a general system, you have hardware, firmware, OS, and software, these multiple layers. All these layers working together during the error handling. If we simplify these, the error handling we're thinking about, it belongs to 4 steps. The error detection, error reporting, error information collection, and also mitigation of the error. Okay. Do you still remember those 3 pain points? Performance degradation, NTF in the RMA, and then the last one, scalability. So because of those, we're thinking about for the platform hardware error handling. For the requirements, we think for the error handling, it has to be performant. The error handling mechanism should minimize the performance impact and maximize the uptime for the system. The error handling should also be actionable. It should speed up the failure through identification, and the result of that should help the action for the operation team. Error handling should also be scalable. We have to ensure the solution is unified and consistent across different vendors and platforms. That way, it's much easier for operation team to operate in a consistent way. Okay, so error handling is actually a very challenging problem because it involves so many different layers. But within the community, we think this is a problem. If we share and collaborate, it becomes easier. So you may have a question, where Facebook is. So this is the current status of Facebook's work. In early of this year, during the OCP Global Summit, we shared some of our work. We started from the number one, the performance part. The work we have been working on is minimizing the performance penalty across associated on the platform associated with the SMM. So there are some more details in that presentation, and it was achieved through some firmware improvements to minimize the performance impact. It's still there, but yeah, much improved. Currently, we spend time after that summit working on looking at the higher layers beyond the firmware. What can we do to improve the error details, especially during the failure through isolation, to help the RMA? Okay, let's take a look at the traditional, let's say this is an example, memory correctable error handling. Traditionally, Facebook is using the SMM-based approach. So BIOS will report the error through SMM approach, and then the error information will be reported and saved into system event log, SEL, in BMC. When we have to make decision from the software side, it actually reach out to BMC, collect the information, and then make the decision. This is the traditional approach. What's the challenge here is actually include two areas. The first one, SMM is actually expensive. And for user, any of the performance impact is always a concern. And then the second thing, improvement on these is always in the firmware layer. Yeah. For anything you want to scale up on the firmware stuff, it's actually very hard, cross-vendor, cross-platforms. So those are the two major challenges we are facing. Another approach is the host-based in-band reporting. We're using the Edik Driver to report the same signal information, but it's on the OS layer. So the benefit of these is, one, it is on the driver layer, much less performance impact to the system. And then two, it's much easier to be modified and deployed across the multiple platforms within our data center. So throughout this work, during the implementation of Edik Driver into our data center, we also see some challenges, and I'll save that for Anil, and he will talk about more detail. Okay, what are the enhancements we get from these? Okay.
Thank you, David. So, how many of you have heard about Edik Driver? Okay, few of them, yeah. So, Edik Driver really is error detection and correction. This was something introduced more than 15 years ago. Most of the work was done by the HPC community. And there are key three things here. It's an open source Linux kernel base. So that aligns very well with the OCP paradigm, open. Also, the main purpose for introducing Edik Driver at that time was for memory error reporting. And also there was some of the PCI legacy error reporting also. Although the name is error detection and correction, but the correction part was, so far has never been implemented, only reporting. And the third thing is it's a platform agnostic. It's a fully in a kernel. And of course, it need to know all the register level details of the CPU, but there is no SMM dependency or any other platform level firmware dependency. So these three key attributes aligns very well with the OCP concept, as well as the 3 requirements as David mentioned, that it should have a least amount of performance impact and actionable. So through Edik Driver, we can collect a lot of information and make it more actionable. And I'll talk a little more on that. And the third one was scalable, because it eliminates the firmware dependencies. So therefore, it's more deployable across multiple vendors with a uniform driver. And from Intel point of view, we have been supporting Edik Driver right from the beginning. And recently, like in last year, we introduced a address translation DSM, and I'll talk a little more about that in the next slide. And today, we are announcing that we did some more enhancement to address one of the problems that David shared on the earlier slide about the memory character error reporting. So let's look at some of the challenges. So the first challenge was, of course, Edik Driver is platform agnostic, but still the actual information is coming from CPU. And there are lots of CPU SKUs or generations. Edik Driver need to comprehend the error registers where the information to be collected for every CPU. Now, that was fine. The next thing was DIM ID. So once let's say we collect the machine check logs, and now we need to do the translation to find which DIM is showing the problem, that requires a translation, address translation. Now the address translation again becomes very platform centric. So how do we solve that problem? So Edik Driver solved that problem by getting approval from Intel, or Intel approved to open source or take some of this internal architectural information registers and make it available as a part of the upstream to the kernel. That was good for one platform, other platform, second platform, but it was not very scalable for us. So how do we solve the problem? The way we solved the problem was using this DSM approach. So we built a DSM. Now, in the beginning, when the DSM was introduced last year, it was still based on an SMM. And recently, we actually changed that to avoid the SMM also. So there's no SMM dependency. Now what happens is that Edik Driver does a call, and the platform does a translation and present the DIM ID information. So now the Edik Driver is completely independent. We eliminated the platform dependency or disclosing some of the confidential information in the public domain. So it's a win-win situation. The second challenge, so DIM ID is there, and so it can get to the DIM as a field replaceable, but the DIM is also made up of 18 devices. So no defect found. So what happens typically is the DIM fails, and the data center, we take the DIM out, send back to the DIM vendor, and guess what? DIM vendor does the testing, no fault found. Because it was so unique to that particular workload and environment that you can't duplicate the problem. But the problem is still there. If you can find precisely which DRAM device, what type of fault we were detecting, then DIM vendors can go and run some workload and some additional testing and find that modularity, find that actual fault. So the challenge that we want to solve here is how to get the precise DRAM information in addition to DIM ID, and then present to the at the operating system level, and then from there to the rest of the ecosystem. So that's the enhancement that we just recently added. Again, the challenge here is, so this is the enhancing the Edik Driver. So what we did here is, in addition to the DIM ID, and then machine check from DIM ID right here, what we did is we added these register details, retry, read, error log registers. Now this information actually has, of course, this is all just nothing but bits, but it has tons of information. This information can provide within this DIM which device was having a problem, and within the device, which bit or which row was having a problem. And of course, the correctable counter. So these counters were not there before. So we added that also. So this is all the new information that we added to support one of the key challenges that David was mentioning earlier. So enhanced Edik driver is developed to capture additional DRAM device specific error logs. Now, once we get this information, tons of machines out there, right? Let's say Facebook deployed, once they deploy that, then we'll be getting this data in megabyte or gigabytes of worth of data, right? So how do we decode it? Now that will require today, that will still require some Intel confidential address, the register translation. As I said, those four registers right there, that contains tons of information, but somebody has to decode it. So today we still will be requiring a translator or decoder that Intel developed, and we'll be sharing with most of the cloud vendors and anybody who has a NDA with Intel. Down the road, we will solve that problem also. So we're taking baby step. First thing is deploy this, see how useful it is. We believe it's useful, but let's deploy and see, and really do a proof of concept. So basically what will happen here is that this data will be fed into a decoder, which may be Python script or some sort of a kernel, maybe part of the Edik driver itself. And it'll do the translation from all these bits to simple thing. What device, what was the bus number, because each device, when we read the whole cache line, there are 8 buses, if you're familiar with the DRAM protocol, DIM protocol. So which bus and which bit. So this simple 3 things can provide us tremendous information about precise fault location. And of course, rest everything is all available already, legacy stuff. Edik driver already provide that, DIM ID, channel, and rank, bank, row, and column. Now, there are some people who say, hey, we already have a row and column. We can point out precisely the cross-section of row and column, and we have the information. Guess what? No. That'll tell you only up to the cache line boundary, 512-bit. If you want to go dig into the whole full cache line, 512 bits, that's where you will need this bus and bit information and device information. So that's something we did today, and now this enhanced Edik driver patch is already out there. I have the link also in this presentation. Once you get it, then you can download it. We are not going to stop there. We have a lot of work to be done here, right? So first thing is we will remove the platform dependency, something like we did for address translation. We'll do the same thing for these retry error log registers. Today we will need a decoder, but then we want to do it through DSM. And the decoding, we will either put it in the platform code itself or through ASL code. Therefore, Edik driver doesn't have to do that translation also. Now, then Edik as stands correction, error detection and correction. So far it's all detection and reporting only. We want to enhance Edik driver further and implement some of the correction capabilities also. And what I mean by correction here is that some of the RAS concepts like DIM map out or rank map out or some region map out concept when there's a failure, persistent fault, that's all done today in the platform at the firmware level. Now that something becomes very machine dependent or platform dependent. If there are 4 vendors, each vendor will have something different. So how do we standardize that and make a very uniform implementation? We can do through Edik driver at the OS level. So that's next frontier for us to start implementing. Now that will require we will still require platform interface, because there's a lot of complexities at the platform level that OS will not have access to that. And we don't want that also. So we need to develop a software firmware interface. Now ACPI exists today, API, right? That's not sufficient. There's a lot of enhancements are required. Because API, if you notice, this is a one-way street. When firmware has some problem, some event, it can notify. But if OS wants to do it, it has to do some sort of a polling method or B2 SMM concept. So it's not a very clean solution from a cloud point of view. So we need to do some more work here. So that leads to what are we trying to do from an OCP point of view. In order to meet some of these key requirements that earlier we discussed, what we need here is develop the actual collaterals. Hardware fault handling design requirements, so that each vendor, the whole ecosystem, whether it's a server hardware or the BMC firmware or SMM or any other kind of firmware or any other component, they all are looking at the same requirement and developing the platform accordingly. Now, this being a very platform, the whole system level concept where all the 4 layers are involved, we need to have a very unified, integrated validation approach also. So validation requirements. How do we validate a given fault handling concept? We need to have a way to inject a fault to verify the flow. Now, injecting fault is again very platform centric. So how do we harmonize that? So that's the validation requirement concept that we want to work on. Now, this is all something that Facebook, Intel started. We have, I would say, fairly decent requirements so far, but we want to really get more input from the rest of the community. So that's really the main thing, that key takeaway from today's talk is, first thing is, go ahead and download this patch that is already upstream now. Tony Luck, so note this name is here, right, in the patch itself. He is really our Linux RAS architect. And so you can download that. And then second thing is contribute, collaborate, help in developing these requirements. And you can contact Zhengyu or David or myself. So today we are just kind of bringing this thought process from now onwards till the next summit in March. We want to see a progression here, to at least see a line of sight to release a 0.5 version of these requirements. And then we will also work on developing proof points, some POCs, and of course then rest of the community, the ODMs and OEMs will hopefully start adopting that. Thank you.
Yeah, so I have a question about error injection concept. So actually, the error injection ACPI table, it's not sufficient. I mean, when I was thinking about RAS, I thought it's pretty standardized interface. So I'm just curious why it requires such changes. So maybe to be precise, what about error injection?
Yeah. So since you're familiar with the ACPI EINJ table, right? There are only 5 or 6 type of errors that are defined there. And if you look at the platform complexity today, there are roughly 20 to 30 types of errors, at least in Intel platform, we can inject. So
yeah, so I wonder if it will make sense to enhance the specification.
So that's what we need to have a little more brainstorming. Within Intel, we have brainstormed this a lot. There's a school of thought that, okay, let's just go and update the EINJ table. Okay. Now, the challenge, every possible solution or approach has some challenges. So updating EINJ table, and Sarathi is sitting there, he knows a lot more about that. The thing is, we need to get approval through the whole API or the ACPI community if you want to make even a single change. And that's a very long cycle, right? So then second thing is maybe develop a TSM approach. through the DSM, OS can query, hey, what kind of error injection capability you have, right? And then ask for error injection with giving all the parameters, and platform will inject the error. So that's another approach, right? Third approach is directly open up all the registers like the way traditional Edik Driver we have been doing that, and just go straight right to the registers, inject. Of course, there is a security issue there with that. But if you're doing in a lab environment, it's possible. So there may be some other ways also to inject error. So we really haven't come to a conclusion. Right now, what we do is we do in the lab environment, and we just use our own internal tools to open up all the injection registers and inject. But in a cloud environment, in a large-scale deployment, and injecting fault and validating in a large cluster, that problem is not solved yet. So this community, this forum, I'm hoping that we will at least drive towards one common error injection capability, which should work for Intel, competition like AMD, ARM, you name it.
Yeah, I also want to add something from the user, let's say from the hyperscale data center perspective. So we always have the same question, let's say when we have a new platform, okay, how do we test, how we ensure the error reporting, everything is good. So fundamentally we need error injection. It's always coming to our mind. But throughout all these generations and the multiple different platforms, one of the challenges we can always say, okay, this specific platform, talk to the vendor, find out the detail, and then work together with ODM to implement. But then when next platform comes, or from a different vendor, from a different ODM, the implementation a lot of times is different, or small changes, but it's still different. We have to verify the methodology again. So I think if a general spec can be generated, then it will help all these efforts.
Okay, so I still have microphone.
Okay.
And what about the other types of errors? We are talking about memory only. What about PCIe? And actually, I'm not sure what is the EDAC level of support for other type of errors.
There is none. And we need to add that. Yep.
So PCIe is a good part. So our March, that presentation in the Global Summit, we actually talk about the PCIe, and that's where we actually find some opportunities to minimize the performance impact. And also that's one of the reasons we try to find a different one this time to talk about the memory. But from our side, I think yes, PCIe, memory, those are the big ones. And then the one from, let's say, processor error. Yeah, that's also a big one.
Mm-hmm. Yeah. Just one thing I will also just kind of follow on to your question. We gave example of Edik Driver today for the memory corrected errors. Now, Edik Driver is not the only solution. This is one in our portfolio. So as a part of requirement, we want to put together a portfolio of the solutions. Because for PCI errors, for example, our ACPI AER, Advanced Error Reporting, that Linux kernel already supports that today, might be good enough. We don't know that. I mean, we know it, but we want to hear more. And there are some more errors in the PCI domain. There are additional errors are being added all the time. So how do we scale it? Again, this whole AER concept is a very archaic concept. So we want to have it more resilient or agile software, the stack architecture. So maybe Edik Driver concept jives very well with that. We don't know yet.
Okay, thanks.
Thank you.
Thank you.